All right, welcome everyone to today's a16z crypto research seminar. Very happy to welcome Roger Wattenhofer, a longtime rockstar professor at ETH Zurich, but recently joined Anza as the head of research, and he's going to tell us about what's looking like the next generation of Solana consensus. So, Roger.
Thanks so much, Tim. Yeah, hi everybody. Great to be here. Great honor to talk with you guys about Alpenglow. So this is really, as Tim said, the planned next consensus protocol for Solana. I'm Roger Wattenhofer, and I did this together with two of my colleagues, Quentin and Kobe. Should deserve a lot of credit for this. So let's start with something, a little bit of philosophy. So you might have heard this quote. If you're like an older person, then you have heard of this probably. This is some what people talked in the 80s and 90s, that in 1940-something, the boss of IBM back then said that there's only going to be a market for maybe 5 computers in the world. And actually when this quote got popular is when computers got popular. Many people got personal computers at home. And people laughed about this quote. Actually, he probably never said this, so this is just made up thing by the internet. But people back in the day said these things, and I'm going to fix this quote for you by just moving this one word worldwide to the proper place. Okay, so I think we're going to have maybe 5 worldwide computers in the world. Okay, so this is what essentially a blockchain is, a smart contract-enabled blockchain, where you basically want to have a world machine, a world computer, which not only serves data like the internet, but does computation for you in a safe and secure way so that you can use it for all sorts of applications. When I think of applications in this domain, it's like maybe with quantum computers, right? I don't think that these world computers will do all the things. There will be still a lot of room to have personal computers, personal devices. But for some applications, this is sometimes the silver bullet to go there. And I think of things like, for instance, big financial systems. There was this GameStop case at some point where the rumor was at least that the people controlling the market kind of, also had some sort of their hands in the game, and then other people didn't like that. So we want to have something which is a safe machine where people can do transactions with that machine, and they are, not abused by those who actually run the machine. So this is one example, financial systems. This is the current example where everything happens. But other things, other very big projects might benefit from such a world computer. For instance, democracy, right? You can have something like, even though XKCD makes fun of this, but I actually believe that something like a blockchain or a world computer can help democracies and elections. Good. So that was my philosophy slide, so we should go right back to Alpenglow. So this is to give you a bit of a backstory. So we started this Anza research. So Anza is sort of like the engineering firm of Solana. And back in December, just a few months ago, we started to have this research team. That's myself and also Kobe and Quentin, I mentioned before. And then if you look at this blog post here, you see that we are from ETH Zurich, and like for crypto people, actually that's a huge red flag, okay? They immediately think of that as Ethereum Zurich, okay? So I have to usually explain, and this is what this slide is for, that actually means something else, okay? It basically means university. Sometimes it's quite a good university. I mean, you guys here in the audience know that because you're academics, but crypto people don't know that. So I found this thing, cherry-picked this computer science, from Wall Street Journal, that they actually were top of the world at some point. I only found one of them, so it's still cherry-picked. Cool, yeah. So we're operating out of Zurich, Switzerland. So here you see our window back then, and you see an actual Alpenglow up here. That's where the name started. So what we care about is performance, okay? So this is basically what we mostly want from Alpenglow. So this is the end of the fun introduction. Let's go to what crypto people, blockchain people really care about. So they have this saying here: increase bandwidth, reduce latency, popular with the Solana folks. So let's first look at bandwidth, okay? How does the state of bandwidth look like? I have this very scientific slide here. So bandwidth is how many transactions per second do you get through, how many bits per second do you get through, okay? And Solana's Turbine protocol, the one we have right now, is actually very good regarding bandwidth, okay? So they basically, I would say, nailed this. They are sending the data, the more bandwidth you add to your system, the more machines you add to your blockchain, the more bandwidth they bring to the blockchain, this is actually helping the blockchain. And it can even be heterogeneous, so it's very nice. More traditional, conventional protocols, they would usually have this leader, and the leader would do a lot of work, okay? So the leader would distribute the data basically to everybody else, and that's essentially a bottleneck that you have. Or they would have some sort of gossip protocols, which still means that the leader basically has to pump in the data into the gossip protocol and kind of usually hurts bandwidth in some sense. So you can see on my scientific slide here, this is much worse than this. Then there's a bunch of modern, I would say, DAC-based protocols. And don't think of this really as up to scale dimension here, but I do believe that they probably cannot quite get to the point where Solana can get. And this is a bit of a bold statement, and I don't have proof for it. But the reason I'm saying this is that this is actually working well with, let's say, heterogeneous environments. So here you can have multiple machines which bring different bandwidth to the table. You can basically sum it up and then divide it by the number of machines which have to be served. Whereas here you sort of need, I would say in the protocols at least we have today, you sort of need a homogeneous environment that all the proposers are basically getting the same traffic, okay? That is kind of balanced with traffic so that you can actually use the bandwidth that you have. So I don't think you can quite get here. So there's Alpenglow here. So I put it a little bit to the right of Solana, but not much, okay? So we maybe can make a few efficiency tweaks there, but it's not going to be much better than what we have today. So let's go back. So I would say when it comes to bandwidth, it's a little bit optimized, but not much better. The big difference is in latency. Let's look at latency. So this is, I can define latency now as something like when you put a transaction onto the chain, how long does it take until it's finalized, until it cannot be reverted anymore? So that's how I would define latency here. And Solana kind of claims to have finality in 12.8 seconds after something like 32 blocks, each block being about 400 milliseconds. That's how you get this time here. But they also have something they call optimistic confirmation. So this is just when you see enough votes for a block on the blockchain, they would consider it basically guaranteed to be in, okay? Even though it's not exactly like that, okay? So at that point, after 500-600 milliseconds, you don't really have a guarantee here, but you kind of can be almost sure. And when you talk to Solana people here, they would usually tell you that this is so sure that it almost never happened that this was reverted again to not being in the blockchain. But it's a bit an apples versus oranges comparison, right? Kind of like, what do you really call finality? Alpenglow here would have a very low finality. It would be super fast in terms of when you put a transaction in the block, at what point is it confirmed? So we claim something like a median finality with 150 milliseconds. This is with the current stake distribution of Solana. So it has some sort of favorable stake distribution that gets you this kind of finality. And but there's sometimes a bit faster, sometimes a bit slower. This is a simulated result when you just test our Alpenglow code with the current system. And well, this I would say will be an apples to apples comparison here. Let's look at the competition again. So some blockchains of course have really bad finality, right? So if you it would not be on the chart, it would be way downtown, so to speak, or uptown, I'm not sure. But the best known competition has something like 400 milliseconds, I would say, self-reported finality. And even that is a bit difficult to compare. I would say this is an apples to apples comparison, but it's kind of like a little bit a different apple. In some sense, I think these numbers here are reported a bit favorably for the competition when I look at them. So for instance, they don't, not every node has the same finality. Some nodes see transactions faster than others or see the finality faster than others. So in some sense, this is favorable for them. But then sometimes it's also not favorable, especially because Solana currently has a nice stake distribution where a lot of stake is somewhat concentrated geographically in similar places, in Europe in particular, whereas they don't have this. So to make comparisons here, and I would say scientifically, that's not really fair, okay? So it would be important that we actually compare the same things. But I don't think there are actually scientific studies which do these things. But no matter what, we're going to have a super fast latency, that's for sure. Yeah.
Can you mention what that computation is?
So these would be like DAG. So the question was, what is the competition here? So these would be DAG-based protocols, essentially. They are the ones which are reporting close to 400 milliseconds. So when it comes to latency, we are actually much better. You know, you could say no matter how we measure, we set a new standard here, but I think the more important thing is that we actually could probably see new applications based on this, right? There are some applications which really demand very low latency, and I think if we go to the 150, so to speak, domain, millisecond domain, then we can do other things like gaming was mentioned, for instance, or just, better financial systems in general. But, okay, so performance is not everything, so let's look at something which is also super important, which is security. How can we make sure that this is actually, a safe protocol? So for Solana, Alpenglow, we have something new, something we call 20+20 security or fault tolerance. So the traditional thing in distributed systems is to have this 33% fault tolerance against arbitrary malicious nodes. And research shows basically that this 33% is the best you can get, okay? So you cannot really go lower than that. But we have 20+20, which is, when you do the math correct, 40. So how can we get better than 33%? And the answer is that we don't have security against arbitrary malicious attacks, but we have security against, different types of failures, so to speak. So we only have 20% security against arbitrary, malicious, colluding enemies. So 20%, up to less than 20%, I should say, of the stake can be controlled by the adversary, which colludes in arbitrary, malicious ways. But then we have an additional 20% fault tolerance against crash failures, okay? And we have a combination of those two things. And this actually happens quite a lot. So you have misconfigurations of machines, maybe. You have something like power outages, like we just had that in Europe. Like all of Spain is basically out of power. And you're going to see this, in my opinion, this is going to, much more of a real problem for blockchains than this is. In particular also because usually malicious attacks, they can be, we can discover that this is happening, okay? We can prove that this is happening. And there could be some sort of slashing, okay? So we could say, we slash your stake if you're going to do this, okay, on purpose. So we currently don't do that, but we could do that in the future. And so then, of course, immediately 20% of the stake at Solana currently is something like $13 billion or something like that. So it's a really big number, right? So you risk a lot of money if you do that. So people probably will not do that, and they will rather see more on the crash failure side. And then finally, and that almost is the last simple slide I have, and then I go a little bit deeper into the protocol, is we want to keep things simple, okay? So a simpler protocol is a better protocol for various reasons. We want to, improve it and maintain it in the future, and then, of course, simplicity helps. It's also easier to prove. So, and I have a little meme here as well. So these are like, two recent rockets, and like the current system of Solana is a very, very complicated machine, okay? And I would say our system is a more efficient machine, but it's also in some sense much simpler. It's still complicated, okay? Don't get me wrong, but it's in some sense easier to understand. Good. I have now a few slides which just compare the current Solana system to our change, and then I go deeper into the protocol. So the few slides are probably motivated with this meme video. You might have seen this. This is the Argentinian president, Milei. He probably is popular among crypto people. So this is him on a whiteboard basically ripping off ministries in Argentina which he thinks are not necessary anymore. And so I did the same. So this is basically our Solana whiteboard with current, I would say these are the main ingredients of the current consensus protocol. So in particular, we have this Tower BFT, the consensus protocol itself. We don't do this anymore. This goes away. Afuera, I would say, if I was the Argentinian president. We have a proof of history, which was, I would say, a core concept of Solana, but now it's also history. Then we have gossip protocols. So this is basically what many blockchain systems have, that they send messages between nodes in a gossip-style way, where they have some sort of virtual network where the nodes talk to each other. So this might still stay for a while, but the consensus part that we do actually doesn't need gossip anymore, so this is gone. And finally, we have Turbine, which is a data dissemination protocol we really like. That's actually, I would say, one of the main reasons Solana did so well so far. And even that, we're not going to remove that, but we're going to replace it with something called Rotor. Okay. So that's our new data dissemination protocol in Solana. And it's complemented with, I would say, voting-style protocols. And we looked into the research for that, and we tried to get the best ideas of recent papers. And in particular, we looked at the simplex consensus protocol and versions of it, I would say. And we looked at something like Banyan, which has a good fast path implementation. And we looked at these things, and we're basically motivated by these things. So what Voter is taking some of those best ideas. And I know now in the room there's many consensus experts which would say, why didn't you this or that way? But we had to make a decision at some point, and this is sort of where we ended up. So Voter and Rotor are two systems. The voting part and the data dissemination part, I'm going to explain them quickly to you. So let's open up with first Rotor. Yeah, that's nice. So this is the data dissemination part. So as I said, it basically comes out of Turbine, and the name Rotor comes from, this is a multi-layered protocol so far, the data dissemination. It's kind of a tree where the leader would send data to other nodes, which then would send it to other nodes and so on. It would be a real tree so far. And we remove the tree part. We make a single layer. So we basically remove all this from this turbine, and then it becomes a rotor, like a rotor in a turbine. So how does it work? Okay. Finally, some technical slides. It doesn't get much more technical than this, but that's how this works. So we have a single layer where we have a current leader. So we have a current node which collects transactions and puts the transactions in a block. I should say that this is already something that we do in a pipeline fashion. So the block is basically sliced into what we call slices. And then we send slices out every so often. A block takes about 400 milliseconds right now. But then it might consist of a dozen or so slices, or maybe even more slices. And so the leader sends out one slice after the other of data. Now each slice, and this is only a picture of a single slice, is made of shreds. Okay, so we have these shreds. So here we have green shreds and red shreds in my picture. This is like the classic way how Solana works. So you use erasure coding, and you split up the slice into shreds. And these are the data shreds. So together, if I just if I basically take the data shreds and just concatenate them, then I would have the slice back again. But then there's also coding shreds, which are basically just the erasure-coded other part of the slice. So what this means is that if you get half of these shreds with the erasure coding, then you can put the slice back together. Okay, so that's the idea. So you have a sort of expansion rate of a factor of 2, roughly. And then this is sent to relays. So now I'm talking about Rotor again. So the leader makes these shreds, makes the slices, then makes the shreds, and then sends the shreds to the relays. And then the relays are just nodes in the system, which then forward the shreds to everybody else. And as I said before, in Turbine, the shreds will be forwarded along a tree. And now the relays are sending the data, these shreds, just to everybody in the system. Okay, we think of having something like, in the paper at least, we think of 1,500 nodes in the system. Currently, I think it's less than 1,300 nodes in the system. But this is just essentially the simplest transmission. You can just a loop where you transmit your shred to everybody. Okay, so that's the simplest thing you can do. This sounds like a huge overhead. When I first thought of these things, I thought this is actually a mistake, right? Why would you just send one shred to just everybody like this sequentially? But this can be done in a few milliseconds, right, with the kind of bandwidth that every Solana node has. And so a few milliseconds is actually much less time than just sending a packet to a geographically different location, okay? So in some sense, that's actually much faster to do it that way. However, we could use some other systems that basically give you something like a multicast system. And there's a close collaborator called 00, which gives you exactly this functionality. So this is essentially how this works. We change a few things here. So one thing we change is we will not send these data shreds anymore. We just send coded shreds directly. Okay, so every shred that we have is coded. The reason for this is that if you send actual data shreds to somebody, then this person gets, in some sense, an advantage because they see the actual data earlier than others. Now, with just sending coding shreds, you just need half of the coding shreds to get the data back together, and the game seems to be more fair at this point. We're also gonna put rewards in here. So far this sort of job, even though it's by far the most bandwidth-heavy job in the whole system, is not really rewarded. So in the future, we really want that every part of the blockchain system, every role you take in that blockchain system also gets rewarded, okay? And so we have to basically send some rewards there. So this is something which is not trivial, I would say, and let me spend a few words here, even though I don't really have slides for this. But so the idea is basically that we're going to do reporting. So what we have is we have these blocks being sent, and then what we have is our so-called epochs. So far, these are 2 days, roughly, of blocks. Every 2 days, we have an epoch. In the future, this will only be something like 2 hours. So we have a 2-hour epoch for which we send blocks out. We do this kind of job here, and we report on other nodes at the end of this epoch. Every epoch, everybody does some reporting. So how this works is that every node who gets these shreds from the relays, just at the end of the epoch says, from which node did I get how many shreds, okay? And so then this goes into a program which then does the rewards, okay? So basically, we want to make this as fault tolerant as we possibly can. And I think this is one of the places where there's still nice room for research because we don't quite know how to do that well, okay? So of course, there's an incentive in the system now to misreport, right? If you don't like somebody, you just say, I didn't get the shreds from that guy, or vice versa. If you like somebody very much, it's your friend or it's yourself even, right? Then you can misreport on the high side that he said, I got much more than I thought. So we have to, we can do many things here. In particular, it doesn't make sense to report much more than you could have actually gotten, of course. You can only get as much as this guy sent, and everybody knows how much was sent in the last epoch. But even reporting on the low side, we want to discourage somehow, and we have a few ideas how to do that. One idea, very simple, is to just say, let's look at the median, for instance, when it comes to reporting. Like, let's look at how many shreds did the median stake, for instance, when you look at all the staked nodes got from that node. So that's one of the things we are doing. But I think we're open for new ideas here. Another thing I can quickly mention here as sort of like a researchy question is how do we actually choose those relays, right? So the principal idea is that to choose these relays according to stake. So if somebody has more stake, then we choose this node more often. And that would help security because if I make the counter argument, then it's very easy to see. If the relays have essentially no stake, then that you choose, then basically they are not really invested in the system, right? And so they have no big incentive to forward the shreds. But high-staked relays, in some sense, are invested in the system, so we should choose them with a higher probability. And the most secure thing we can do is to choose everybody with the probability according to their stake, okay? But now, there's still questions, right? Do we want to do this with or without replacement, okay, for instance? These are two things which have exactly the same expected value. If you choose these relays with or without replacement, you can do it with the same expected value, but the variance would change, right? In particular, if you do Without replacement, in some sense, the variance would be lower, which is better because everybody's going to just be chosen once or 0 times, right? If you have with replacement, then it's then the spread of how often you're chosen in some sense is higher, and that also increases the variance. So, but we really want to have the lowest variance version here, and this is neither with or without replacement in the naive way, but we gonna basically mix this up with something which is deterministic. This is an idea which has been done before with the fait accompli version of choosing such participants in such a system. And we looked a little bit into this, and we felt that maybe even more is on the table for this. Okay, so we haven't written a paper here, but I think this could be just an academic paper, which is part of this Alpenglow, system. We looked a little bit. This is now the simplest thing we could do. We just looked at basically simulations of this system. So we have here 2. So whenever the background is white, then this is basically very close to the paper, I would say, and close to research, because I didn't care to make it nicer so far. But these are just some simulations, basically, and we have here, let's say, 64 shreds in total, of which you need 32 to build the block together, right? And now you can think of having nodes which don't forward their shreds, right? You can have 40% of the nodes not forwarding the shreds, 30% or 20%. You cannot have more than 40% not forwarding because we assume that 60% at least are not crashed and actually correct, but we can have all these things in a very bad system case. And then is the question, if the adversary now comes and corrupts some of these nodes with that much corruption power, let's say, what's the probability that you don't get the block together, okay? And this is a bit more complicated because you can basically, every slice of the block could be corrupted, and then the probability for the whole block to be corrupted is just if a single slice is corrupted. So you very quickly get very high numbers of corruption, surprisingly high numbers of corruption. So let's look at this one here, for instance. So if 20% of the nodes of the stake are not forwarding their shreds, then you can see if you look at the way Turbine is doing it right now, then you have this probability for the block to fail. So 10 to the minus 6, maybe roughly, a little bit less even a bit worse. Or you can have a stake weighted just with replacement as is. Then you have the green curve. Then you have this fait accompli, the first version in that paper, that we get that much. They have a second version in the paper as well, which we did not implement so well, I think, but it's a little bit better, but not much better than FA1. And then this is our version here, which chooses essentially, does something similar to fait accompli. Basically, if a node has so much stake that it will be chosen multiple times as a relay in the system, then we would choose it exactly deterministically that many times. So only for the remainder, so to speak, where it's not a full relay that makes sense, then we start to use the probability. And for that, we do some sort of partitioning system that we take all the probabilities we still have. We have the number of rolls we still need. We have the probabilities. And then we choose, we bucket them. And then we choose one per bucket, essentially randomly. So that's roughly a high-level idea there. But I think there's still some things on the table. It's clearly an NP-complete problem because even what we do would use partitioning, which we cannot solve perfectly. But I think it's an interesting question.
So for the validators who, in expectation, be chosen once or more, you're saying you just round up or down.
Yeah, we round down like to, let's say, if somebody is chosen 1.7 times in expectation, then we would always choose this node once.
Okay, and then the
0.7 goes into the second part.
And you're saying then you do bin packing on the things and choose one from each bin proportional to the, okay.
Yeah, we bin pack then for these little percentages, and then we choose that according to the proportion. And that at least got us, somewhat better.
And these are experimental. These are reports of experimental.
These are results. This is just simulation results. We just simulated the system, and we don't have, let's say, real bounds so far, like how good this actually is. But And you can see the numbers get really bad if you have a high attack angle. I mean, we need 50% of the shreds, right? And if 40% is crashed, then there's still already a chance that you don't get the 50%. And then for each slice, we need that, right? So that's why these numbers here basically become very bad. And it would get better, for instance, if we keep like this kappa here, just means the same ratio between how many shreds we send and how many shreds we need. So we have a factor of 2 over-provisioning still here. And we have the worst case of crashes here. So that is the same. This is for 64 shreds, so the same as here. So this is the same curve as this one here. But then if we added more shreds, then this would actually help our cause. So this is just 2 examples of things we are currently still looking at, like this sampling strategy here on the one hand, and on the other hand, what I said before with the rewards, right, which are also not yet fully clear. But I would say many blockchains have this problem still, right, that you as a node, as a participant in a blockchain, have to put in work, and not all the parts of the system are rewarded usually in blockchains. Okay, let's say gossip is the most classic example, right? And gossip usually is not rewarded at all. So why should you do it, right? So we actually have the ambition here to reward all the pieces so that there's very difficult for nodes not to do their job. Good. So far for rotor, and now I go to voter. The second part, so the voting part. So many things change here, and this part in some sense is more complicated, okay? And I show you the main points here. I would say this part, I would really struggle to present everything in a short technical talk because things get hairy. So what we want on one slide essentially is we want, a single leader blockchain where the leader is just rotating over time. So we basically want some leader to propose a bunch of blocks, 4 blocks in my picture here, and this is also the current parameter we have, before handing over to the next leader, which then again proposes 4 blocks. Okay, so that's essentially what Solana has already today, and what we are going to keep in the future. So it's only a single. There's no multiple leaders currently which propose blocks, but just a single leader. Now this has been done with proof of history in the past. But we want to change this to timeouts. So how this works essentially is like this. So we have, at the end of each block, we have every node is a referee. And the referee just says, was this block in time or not? How this works is that every node essentially looks at the last block from the previous leader, if it existed. Let's assume this for a moment, this is the case. And then starts a local, let's say, system time timeout here. And just checks, is this block here, in the timeout, assuming that this node here has roughly correct system clock. It doesn't have to be a perfect system clock, but plus minus 1%. And then can vote, yes, this was in time, or no, this was not in time anymore. If it was not in time, it would be against this block, essentially. We don't do this for just the last block, we do it actually for all the blocks, but we start a timer here. So you now might say maybe this block here did not exist or something. So we have a little bit of a complication to make sure that there's always a timer which happens for the next leader window. We do this for all the blocks because, let's say if a leader would not play along the rules and the first block would be too late, for instance, we would downvote this. So then we have an opportunity to immediately skip that leader. Okay, so if we would have a strong agreement that the leader didn't do the job, then there would be a downvote and we would change to the next leader much more quickly. And that's maybe one of the cases where our system, Alpenglow, would have more bandwidth usage than the current Solana system, which does not change so quickly to the next leader. Okay, but we have this rapid failover idea. Okay, so we have this every node basically, which then up or down votes every block independently. It's not randomly independently because they hopefully have roughly the same time. Let's assume the referee in our case says yes, the block was in time. And now we do the same thing as before. So the node just sends out the vote to everybody else, okay? So that's for that. And what happens next? So now every node judge for themselves whether they got the block in time or not and sends out the vote. And it sends it out again to all the, let's say, 1,300 other nodes. And then, well, this should also be rewarded. This is actually very similar to before, right? So everybody in an epoch would just check how many votes did they get from what other node, right? And report that at the end of the epoch for the previous epoch, and then rewards would be granted based on that. Okay, so finalization works like this then. So you get now the votes from the other nodes, and let's say I just collect the votes based on stake. So the votes count how much stake they have. It's like that before, and you just check if you have, let's say, 80% of the votes being an upvote at least, then you immediately think of the block as final. So what you do is you make a finalization certificate at this point, putting, this can be a BLS certificate here. So you put all the votes that you have seen, all the plus votes, all the OK votes or notarization votes are called really, into this finalization certificate, which will prove to anybody that this was a finalized block. Okay, so that's the idea here. So this is, in some sense, on the one extreme of the spectrum. We can also send this out again to everybody so that everybody also has the same information as you. This is also something we can probably improve a little bit here to make this actually, slightly less bandwidth consuming. This is still on the message, and actually everything I said so far, all the information, so the shreds, the votes, these finalization certificates, all of them fit into a single UDP message, right? They're all very short. You don't need more complicated networking than just maybe authenticated UDP messages or some sort of quick messages or something like that. So on the other extreme, you get something like this, that you get a lot of downvotes for the last block. And in this case, it's also clear what to do. Let's say if you have at least 60% of that downvotes, then you produce what is called a skip certificate. And that just means that the block is considered to be skipped. Okay, so we don't do that block. We just go back to the last block. So you can see it's not quite symmetric at this point. You might wonder why we have these things. And of course, there's a whole intermediate part, also that we can send out to everybody. So when the votes are basically between these two extremes, what do we do then, right? And the answer is for these mixed scenarios that it's kind of like more complicated. In particular, in all these variants in between, we have one more round of voting, okay? So it's not immediately finalized. So here we don't need more voting. If you get 80%, you're immediately done. And here you're also immediately done. But in this case, you need one more round of voting. So now, in particular, maybe I want to make the talk a little bit deeper than I used to make it. In particular, if this is 60% upvote, so very close to this scenario here, then it's basically already what we call a notarization certificate. We would say this is a block we want in, but we need one more round of voting, like classic, I would say, consensus style, 2 rounds of voting to make it final. Okay. That would be another typical case that we would have here, but there could be other cases, and it's a typical thing for consensus protocols that you have to make sure that you have different buckets of what could happen, right? And since not everybody has the same view, you also have to make sure that if you see a bucket, that also the neighboring bucket that somebody else could see, that they don't conflict with each other. That makes this thing somewhat difficult. Good. Well, this is the whole protocol, okay? And this is the whole voting part that we have. So upon things happening, we do things. And so I'm not going to go through it with you guys, I think. But this is what you can see in the paper, and you can read if you want to. And this is the paper, this white paper. But I want to go a little bit deeper for this talk, since I have a few more minutes. So these are just basically all the votes we have. Okay, so the votes I already mentioned are the upvote. This was the notarization vote. So you would say, I vote in that slot. I have seen, this block, the hash of this block, essentially. Or you can have a skip vote that you say, I want to skip that slot. That would be typical. And then you have these fallback votes that we have here, which we borrow from other protocols before. Essentially, when you notarize something, but you see that nothing really can happen because not many nodes notarized it, for instance, you go into this middle ground. Then you can issue a a fallback vote, okay, of the other type, to make sure that with these fallback votes we get enough, votes of certain type to still make a certificate. Okay, so that's the base idea here. And you can have a finalization vote at the end. So if you have a noter vote and you get 60% there, you can get to a finalization vote. So this is actually the second part of this slide. So based on these votes that we have, on the first round votes, notarization and skip vote, and on the second round votes, all the longer ones, we can build up to 5 different certification types. And one I already showed you on the previous slide was the fast finalization certificate. So that's just collecting all the initial notarization votes. And if you get a stake of 80% at least to do that, then you know that this is finalized. And you immediately get this finalization certificate, or more precisely, a fast finalization certificate. And then with 60%, you get the notarization certificate. And then you can, with the second round of voting of these final votes here, you can get a finalization certificate with another 60% here. Or you can get the fallback cases that you say, I take original notarization votes or fallback votes, and they together have to have 60%, and that gives you these notar fallback, for instance, certificates. So this is sort of like what makes the thing a bit complicated. I would say, to prove to you that this is all correct, you really have to read like the 10-page proof that we have in the paper for this. Yeah. Let's look at 2 more little things. Yes.
On the previous slide, some of the certificate consists of one type of message, right? So then you can use a BLS threshold signature or an aggregate signature to represent it. But for the certificate that consists of 2 types of messages, how do you compress it?
Oh yeah, that would, okay, so the question is, what about certificates which use 2 types of messages? How do you make a BLS certificate? And so it would only be, from each node, only one type, okay? So you can say you have either this or that. And we hope that this works, but it's a good question how to do that actually, right? We would maybe have to mark it as a bit. I'm not sure whether we would have to do that, what type it was. Exactly. Yeah. I mean, usually we use a bit vector if you just have one type, but I think maybe for these we might have to mark which one it is. Yeah. I don't even know. Yeah. Okay, so this is to just show you again how this works in time for one round, basically. So the leader sends out the slices, or the shreds in this case, to these randomly chosen nodes, to the relays. And then the relays at some point pick up these shreds, send it to everybody. So this is, of course, overlapping because maybe the last shred was not received by some relay before the first one is already sent out again. And then you get the notarization votes. And you see here, at some point, you have this notarization point where you get 60% of the notarization stake in. And you can say this is now a notarization case. Or you get the fast finalization when you already have 80%. So you just continue collecting until you have 80%. At that point, you would have the fast finalization. Or you have the actual finalization vote. So at some point, whenever somebody gets to the 60%, they would send the finalization vote, which gives you the slow finalization. Now, surprisingly, this is not always in this order, right? So depending where you are, sometimes it's actually faster to do this and then this than to add this part here. And this is particularly the case when you have many nodes together in, let's say, Europe, which is currently the case. Then, of course, they have very low latency between them, and it could happen that actually they see 60% notarization votes very quickly from other European nodes, for instance, and then can immediately go for the finalization. Yeah, one more thing I want to mention. So just a few, things. This is a wide slide, but it's well hidden, so that it's not really wide. So you might wonder about this part. So when you're actually in charge, when you're the current leader, then you send out your block. And at the end, when you're done, you immediately send out the next block. You send out the first slice of the next block because you trust yourself that you do a good job. And in case it didn't work, then you cannot do anything anyway. Then the others will vote you down and look for a new leader. But here there's no gap in some sense. But here there's a little bit of a gap, right? Because the last leader sends out the block, and then the next leader has to send out the block. And what you really want to do here is essentially the simplest thing to do is that the next leader just waits until it sees either a finalization certificate or a skip certificate for the previous block. Because that gives the new leader the understanding on top of which previous block, on top of which parent block the block would be built. But at that point, you maybe don't have it, right? You want to start building your block now, but you don't see it. But what we do is really we do it optimistically in some sense here to make this as small as possible. So what we get is we get the previous block, or the last, as I say, the last slice. This is a slice now from the previous leader. And we immediately start building optimistically a block, assuming that this previous slice here would be confirmed, okay? Would be, finalized. But, and if this happens, actually, this is given by this parent-ready event here, that the previous block was actually finalized, then we just continue building. But in case this is not happening, we might start building a new block here. But at this point, we get essentially from the system notification that the previous block didn't get through, okay, that this is skipped. And this can happen, some slices in, actually, into the next block. And then we would say, but at this point, we know that which previous block we actually can build on top of. And that would change our system. So technically speaking, we keep running, we keep adding slices to the block here. But at that point, we put the parent pointer in here, basically saying who is the parent, and then these previous slices will not be used for the final block. So that's just something very technical. Oops, I'm actually running out of time, which is something I didn't want to do. So let's just go to the last slide I have, which is this one. So this is basically just summarizing everything in one slide. Okay, so we have here what we call a latency histogram. So we have 100% of the stake here of all the nodes in the system. And this is just network latency from, let's say, if the leader was in New York, okay, so what we are currently right now. So the leader is in New York, and you can see here there's there's more stake, which is basically in Solana right now, which is actually also in New York. So these are validators in and around New York. And then you see that the latency starts to pick up. And yeah, so here you have the 200 millisecond line, in case this was a bit too small. And you can see that, for instance, here you have this network latency. Here you have a big plateau. So these are the European, essentially the stake in Europe nodes, which have about that latency from New York. And here you see like some other US nodes in the Solana system currently. And that's sort of a lower bound. That's just pure network latency, just pure ping or just one, not even a round trip time, just one leg of the distance for sending a bit. And that's the lower bound for how well you can get. And now we can look at the rotor, how fast can we actually disseminate these blocks based, how much slower is it? And you can see that it's quite a bit slower for these nodes initially, because basically these are sent to random relays somewhere, and then you have from half of them you have to hear it. So this takes some time here, but it's not much worse actually than the lower bound. And then we have two more curves here. So here we have the 60% curve, which means at this point you get 60% of the notarization votes, is the red part. And we have the finality, the blue curve. So this can be multiple things. So it can be the 80% notarization votes that you get that here. And because of this you get fast finalization. Or it could be that you have a second round with the 60% and you get finalization like that. Or it could even be that you get a finalization certificate from a third party, that you see that one first, right? And it's actually a mix of these things that we see here. I mean, maybe not the last one, but you definitely see 60% and 80% here. Good, yeah. And so this is maybe the last real slide, timeline. So this is kind of, we revealed this Alpenglow just a few weeks back, how this should work. What we have now to do is in the Solana universe, we have to ask for so-called SIMD, where we have to ask for permission to do this from the nodes which have stake in the system. And then there will be a bunch of testing to make sure that this actually works. And the hope is to, at the end of 2025 or maybe beginning of 2026 to actually ship this thing. And that's actually Solana language for shipping things. Good. Yeah, with that, I want to thank you for your attention. And thanks also to my co-authors. This is the link to the white paper.
Sorry, this is from a little bit back. So you're talking about this deterministic leader election protocol, right? Sorry, relay election protocol, right?
Yeah.
So suppose, I've been elected to be the relay for now, and I'm just supposed to be elected once. Then the Solana that I'm staking in some sense is different from the Solana that's staked by somebody else, because it's Solana plus the right to get elected as the leader. Do you think this difference between the different Solana tokens would make a difference somehow?
Okay, I think I didn't quite understand the question. So you're talking about the relay part where you are chosen what is currently done right now and what we do in the future, or?
No. So what's to be in the future is so if I hold 1% of the stake, I deterministically get elected 1% of the time.
Not deterministically by some pseudo-random function, yes. And with 1%, let's say in 64 shreds, you would usually not, there's still a random process how often you will get in or not, right? Only if you have a higher stake than, let's say, 1/64, then you're going to be deterministically in there for sure once.
Sure. I'm 1/64.
Yeah.
And then I got in once.
Yeah.
So I know I'm not going to get in again until other people get in once again.
No, it's not that deterministic. It's really always just random. Like for each slice, basically, or for each block, it's random. But, actually, really for each slice, it's random. But to make sure that in expectation you get what you have as a stake, right?
Oh, it's still pseudo-random.
Yeah, still. So in expectation is still the same. Yeah. We only look at the variance. Actually, the only thing we change is the variance, that you don't have such a high variance how you get in. Yeah.
I wonder, how do the fallback votes and certificates come into the picture of both the network effects and the lines you had, the arrows? Where does that fit in there? And do I consider a block finalized if I see a note or a fallback certificate for it?
Yes, good question. So I didn't say that, right? So the question is, when do I skip and when do I fall back? And in some cases, I could even do both, right? So I didn't really say that at all. So it could be that you can get multiple certificate types for a block, and then in some sense the next leader could even choose whether they keep that block or actually they skip that block. In some cases, you really can have both, right?
Just saying, I could have both a note or fallback and a skip fallback certificate for the same block.
Yes.
And then it's up to the next leader to choose whether the one they want to block in or not.
Yeah, in particular, this is I would say, not very common, but it's kind of the common fallback thing, that if you see, let's say, 50% say yes and 50% say no, then basically both sides could now say, I fall back to the other side, and then you would get basically both the certificates. So these things that I showed here, they're always just showing the happy case, which we expect to be the normal case. But of course, it could be that you get the relays and then you don't really send authorization votes out, but you send, let's say, skip votes out here, and then this would happen essentially in this part, right? That you have a different execution part. This is, I would say, tricky, and there's say the conditions that you have, whether you can send such a fallback, they can be quite complicated, and I would refer to the paper for that. I think it's too complicated to explain here.
And so is this sort of like multiple paths? Is that part of what's inspired by Banyan, or is that?
The Banyan has something like this as well. So Banyan, I would say, has really the multiple paths which start at the same time. I think that was maybe the first protocol. The fast path, this was something that happened before, right? That people would say, let's try something fast. If it doesn't work, then let's try something slow. But Banyan was maybe the first paper which goes forward with both things. Banyan, in some sense, is not practical. It's an academic protocol, but I would say we kind of made this more practical. There's also this Kuzu paper now, which is by a subset of the same authors, and because they also started talking about this. So in some sense, this is sort of like both things, I would say, have this idea.
And why the leader proposes 4 blocks in a row?
Why the 4 blocks in a row? That's a good question. That's actually also, people would maybe not agree. So currently, this is just what Solana has been doing. So we just keep up the tradition, I would say. So it helps a little bit, of course, to have shorter times between leaders or not have that often. But some people would say, let's just do one block per leader and then go to the next block. I think that would be valid thing as well. It's a trade-off between performance and maybe some sort of maybe MEV opportunities because of that as well. Right?
Let's thank Roger again.
Yeah, thanks.